Okay. Are we ready to get started? Sanford Underground Lab.
Good morning to those of you in most of the United States, and good afternoon to those of you who are joining us from the East Coast of the United States and from the United Kingdom. We are coming to you live from the 4850 level at the Sanford Underground Research Facility and from 3,600 feet below ground at Boulby Underground Laboratory in the United Kingdom. My name is Constance Walter. I'm the Communications Director at the Sanford Underground Research Facility. And I want to thank you for joining us for Deep Talks, an international journey to dark matter detection. We're excited to be partnering with Boulby Underground Laboratory, the University of Edinburgh, and the Science and Technology Facilities Council, all in the United Kingdom, for this very special Dark Matter Day. Now, throughout this event, we're hoping to foster a greater understanding of dark matter, which is an elusive particle that makes up around 23% of the universe. And before we start, there are a few people I'd like to thank. I need to thank our Deep Talks sponsors, and that includes Charles and Jolene Lichtenwalner, the RCS Construction Group, and Crow Peak Brewing Company. I also want to thank our Sanford Lab team for their assistance in getting us underground during the pandemic. And of course, all of you for joining us. So now please allow me to introduce our event MC, Sophie Palmer from the Science and Technology Facilities Council. Welcome, Sophie.
Fantastic. Thank you so much, Connie. Hello and welcome, everybody. As Connie said, I'm Sophie. I work for the Science and Technology Facilities Council at the lab that you can see behind me, Rutherford Appleton Laboratory in Oxfordshire. And I'm so looking forward to today's event. We've got a great lineup of speakers and tours. So I really do hope that you enjoy it as much as I'm sure I will. Just before we get started, a few quick housekeeping bits. We'd really love to hear all of your questions. Things. We're going to do a panel discussion at the end. So if you're watching us on Zoom, then you can join. You can ask us questions using the Q&A function, which you'll see normally at the bottom of your screen. Sometimes if you're on a mobile phone, it's up at the top. So you can submit questions throughout the event. Please do. We love talking about dark matter and all of these things. So please do submit as many questions as you would like. If you're watching us on Facebook Live, then you can pop comments in there and we will see those too. And you can also use Twitter to ask us questions using the hashtag AskDarkMatterDay. We'll pop that in the chat in a minute. So please do use the Q&A buttons and things, Q&A buttons, comments on Facebook, and the hashtag to ask us as many questions as you can. There's also a chat function. If you are having any technical issues, pop something in the chat and we will do our best to help you. Okay, so before we hand over to our first talk, we thought that it would be interesting to see what you already think about dark matter. So you should see some questions up on your screen and we would love you to be able to answer some of these. So the first question is, dark matter research is too difficult for non-scientists to understand. So you should be able to press agree or disagree and do fill in those questions, or I can see people tapping those answers in. We would love to see what you think. Our second question is, why do scientists go underground to study dark matter? Is it because scientists need to be in total darkness to detect dark matter? Is it because scientists need to shield their experiments from cosmic rays? Or is it because scientists believe there are more dark matter particles underground than on the surface? And our final question for you is, what % of mass and energy in the universe remains a mystery? Is it just 1 or 2%? Is it 25 to 40%? 72.45%, or 96%? So I'll give you a few moments just to have a think about those questions and to tap in your answers, and then we will see where we go. We will get from there. Lots of people filling out answers. This is brilliant. Okay. All right, so let's see where we are. I'm going to end the polling in 3, 2, 1 now. And let's see what people thought. Okay, so I'm sharing the results. You should see what everybody answered in the polls. So 40% of you think that dark matter research is too difficult for non-scientists to understand. Most people think that scientists go underground to study dark matter to shield their experiments for cosmic rays. And the majority of you think that 96% of mass and energy in the universe remains a mystery. That's fantastic. Thank you very much for sharing that. Now, all of our speakers know where we stand from there. So just to give you a very quick rundown of how today's going to work, we're going to have a number of short talks from some fantastic speakers, and we're also going to go on some virtual tours underground. So our first speaker is going to talk about what is dark matter and why do we go underground to look at it. So you'll see the answer to one of those questions that I just asked you before. So in a second, I'm going to hand over to Dr. Jarrett Heiss from the Sanford Underground Research Facility. So Jarrett joined the facility in 2008 as a science director. And before coming to the lab, he served as the detector manager in the Sudbury Neutrino Observatory, or SNO experiment, at SNO Lab in Canada. And that was an experiment that helped to resolve the solar neutrino problem, which shared in the 2015 Nobel Prize in Physics. So some really, really exciting questions there. Dr. Heiss has a PhD in particle astrophysics from the University of British Columbia in Vancouver, Canada, and has been actively engaged in underground science for 20 years and counting. So I'm going to hand over to Jarrett to talk to us a little bit about what is dark matter. Jarrett.
Very good. Thank you, Sophie. Let's get started. Let's set the stage. For thousands of years, actually hundreds of thousands of years, we've been staring up at the stars, seeking to learn what secrets they hold and to understand our place in the universe. Our observations have inspired big questions, like what are we made of? What is the universe made of? It turns out that normal matter, stuff we know about, tables, chairs, stars, planets, galaxies, makes up only 5% of the universe. In other words, 95% is still waiting to be discovered. Now that's a humbling statement. What were we doing with all that time, those thousands or hundreds of thousands of years? But it's also fabulously exciting because that means the universe is a much more interesting place than we ever imagined. Compared to normal matter, 5 times more matter is in a form unlike anything we've seen. But there's a lot of compelling evidence for dark matter, and we call it dark to put a name to our ignorance. That evidence includes the rotation speeds of galaxies. Also, we see light bending around objects that we can't see. So there are a number of ways to search for dark matter. Scientists produce it at the world's largest particle accelerators. Others search for dark matter using telescopes, looking for signatures installed on sensors deployed on satellites in outer space. Today, we're going to focus on direct searches for dark matter. Before we go further, though, we should touch on why scientists go underground to perform these searches. Our planet is constantly bombarded by high-energy particles from outer space called cosmic rays. They interact in the upper atmosphere, producing a shower of energetic muons that bombard the surface of the Earth. For those of you on the surface right now, hold out your hand. 2 or 3 of these cosmic ray muons are going through every second. Scientists moving underground are able to take advantage of rock overburden. That rock can act as a shield. Here at SURF, that depth is about a mile or 1.5 kilometers. That knocks the flux of cosmic ray muons down by roughly a factor of 10 million. So that 2 or 3 per second on the surface translates into 1 per month at our facility underground here at SURF. And Boulby would be similar. Scientists use that shielding in order to give themselves and their experiments any hope of seeing the faint signals that would result from interactions with dark matter or other rare process events like searching for neutrinos or their properties. In other words, the underground environment produces a quiet that the scientists need, otherwise the noise, that cosmic ray noise, would drown out the small signal that they're trying to see. So hopefully that sets the stage for some of the talks that you're going to hear. You're in for a real treat. We have a worldwide tour, and you'll be visiting with experts on some of the leading dark matter particle searches anywhere in the world. Back to you, Sophie.
Fantastic. Thank you so much. That was a brilliant introduction to dark matter and why we go underground. So I'm sure all of you will now be able to answer all of those questions with a bit more confidence. Do you remember to pop any questions that you have into our Q&A boxes? I've seen some great ones coming in already. We'll get to those really at the end of the session, but we're really looking at, there's some great questions there. So I'm now going to hand over to our next speaker, who's going to be talking a little bit about the past, telling us about the history of direct detection research. And how did these experiments even get started? What have they already discovered, if anything? And why are we carrying on continuing to build bigger and better detectors? So our next speaker is Professor Alex Murphy. Alex is a professor of nuclear and astrophysics at Edinburgh University, where he's been since 2001 after moving back from Ohio State. He's worked on direct detection of dark matter for many years, but he's also interested in stellar nuclear synthesis, so how the elements that make up our world are created within stars. On top of that, he also sits on the science board of our UK science funding body, deciding which projects will get funded. And I happen to know is very good at building Lego Millennium Falcons. So, which you can see just behind him in a second. So I'm going to hand over to Alex, who will share us a little bit about how we've got to where we are. Alex.
Right, hi everyone. Hopefully you can see me and see my slides. I've got some slides to show you. I want to give you a very brief history of the search for dark matter with very much a UK flavour to it. And this opening slide here, you can see there's the SURF facility up here at the top right, and there's the Boulby facility at the lower left. There's also sort of a slightly comic parking space at Boulby indicated there. I actually have this parking sign in my office. I'm very proud of that. And then on the top left, we see a photo of the very latest generation of dark matter experiments, which was being constructed behind Jarrett, as you saw him there, in the SURF underground laboratory. So dark matter, direct searches for dark matter. The very first idea for this kind of came in 1984, where a couple of scientists in Munich had an idea actually for detecting neutrinos, a particular type of neutrinos, sort of low energy ones. And it was an interesting idea. It got taken up in other ways later on. Just a year later, another couple of physicists came along and realized, hang on, this technique might be able to work for trying to find dark matter. And this was the first time that someone had come up with an idea for how we might directly detect the dark matter in the universe. And essentially it's a case of building a detector which is extremely sensitive putting it in a place where you're not expecting to see anything because you're deep underground, and then seeing if it still registers events. So you have to build a very sensitive detector which can see the signals that we're expecting to see from dark matter particles, and you do that deep underground, as was said. So that was 1985. The first experiment to do this, just a year later, actually took place at the home state mine, which is now where the Sanford Underground Research Facility is. It was led by Pacific Northwestern and University of South Carolina and Boston and Harvard. I don't have a photo of it, unfortunately. This was back in the mid 1980s. This is before mobile phones and things. Cameras weren't just so readily available everywhere. I can't find a photo for it. I've asked the lead scientists of that experiment, and they don't have anything either. What I have been able to find, though, is a diagram of the facility at the time, and maybe you can see my mouse, I'm not sure, but at the top left here, there's a large tank which was actually holding the material which was for Ray Davies' solar neutrino experiment, which went on to win a Nobel Prize. But then there's this sort of ramp area. People who are familiar with the underground mine, they'll recognize where this is. And at this top area, just up here, that's where we believe the first experiment was located. Like I said, I don't have a photo of the experiment, but I have another photo of a similar experiment located a little bit later on, which was in that place. And you can see the kind of environment where people were having to work at that time. It's rather different from the rather sort of Starship type environment that was behind Jarrett in his opening talk, where it's all nice and clean and shiny metal. Here it's dark, dirty tunnels and tiny little holes you have to scrabble into. The person there, in fact, turns out to be a guy called Richard Schnee, who some of you may also know. He still works at Sanford occasionally. So that was the very first experiment. Just a year later, in the UK, I'm going to give a somewhat UK biased talk here, a body called the UK Dark Matter Consortium was formed, started by Rutherford, which is where Sophie's working, Imperial College London and University of Sheffield. And they developed, together with other collaborators joining later, I came in at the NIAD phase of the project. They went through and developed a series of experiments, and I'll just show you a few of those, just to give you an idea of what the apparatus looks like and how it's developed over the years. So the first experiment in the UK was the germanium experiment, which was very humble. Here it is. It's just a relatively standard germanium detector. Again, you can see we have shielding. You'll notice that a lot of these experiments have additional shielding built around them. We're shielded by a mile of rock above us, going deep underground, but even that's not enough to get rid of all the background radiation that we want to. So there's then additional shielding going around the detectors, and here we've got lead around it. Again, this is very humble. It's starting with a genuine garden shed. And the person in the photo here also turns out to be someone who people may go on to recognize. That's actually Nigel Smith, who's now the director of Snow Lab. Certainly one of our competitor laboratories, and certainly an excellent laboratory. The NIAD experiment that I got involved in looked like this. It was NIAD stands for sodium iodide advanced detector. The sodium iodide, that's just essentially table salt, but it's a single crystal of table salt, encapsulated again inside very clean copper, and that's inside a lead castle. And it's not so easy to see the scale here, but it's about 3 or 4 feet across there and about 10 foot long. This thing here is about 1.5 feet long. The next one I'll mention is known as drift, directional readout identification from tracks. This one's a little bit different from the other detectors we talk about because it's based on a sort of gaseous technology. It's a much lower density medium. One of the benefits of that, though, is that in principle, if we see dark matter with it, you might be able to tell where it came from rather than just seeing that it's around. It's a directional instrument. This has the rare honor of now being on display in a museum. It's in the Science Museum in London. And it's worth pointing out also that a version of drift is still running today in the Boulby laboratory. We might see a picture of it later on today. The next experiments were a series of experiments called ZEPLIN, with a strangely constructed name to go with them. The important thing here is that these are the first experiments that we used with xenon as the target, as the main sort of element in the detector used for the detection of the dark matter. The actual detector is this thing down here. Again, it's got infrastructure around it to provide extra shielding from the background radiation that we're trying to get rid of. And this is a rather small little instrument. It's a total weight of about 5 kilograms, and it just has 3 so-called PMTs, photomultiplier detectors. We'll probably hear about those later. But these are the light detectors that actually try and read out the signal that gets generated in the xenon when a dark matter particle hits. Oddly enough, this is also now on display. It's in the Polaris House, which is the main building for the UK funding agency, which within science, of course, to us, that's very important that the funding agency recognises what we're doing. Zeppelin 2 have obviously followed Zeppelin 1. It's somewhat larger. It's also now using liquid and gas. This was a really important development because this liquid and gas technology has gone on to dominate the world's searches ever since. And the LZ, as you will find out later, is based on this liquid and gas technology. It's a little bit larger, and it turns out it was about 67% more sensitive than Zeppelin 1. Still didn't see any dark matter, but we could tell that it was more sensitive by a fairly large amount. This is on display, not anywhere particularly fancy. This is within a photograph from within the Boulby mine, and here it is sitting at the corner here, and it's essentially a coffee table. Zeppelin 3 followed that. This was a slightly different design of liquid and gas xenon detector with a higher electric field, as it turned out, more photomultiplier tubes, and again, that was it's sort of in its initial enclosure, but then it's covered with a very large layer of lead to provide this extra shielding around it. That turned out to give a result that was 28 times more sensitive than Zeppelin 1, really a large advance in sensitivity. This Zeppelin 3 has also, I said it was a rare privilege. It is a rare privilege, but for our dark matter detectors, they're so high profile, they are ending up in museums, virtually every single instrument. This one is now an exhibit at the Whitby Museum of Treasures. After the Zeppelin 3 program, it was time for the UK program to merge with the US program, and we joined what was known as LUX, the Large Underground Xenon Experiment. Here's some images of LUX during its construction. It's a larger instrument, it's somewhat more complicated. It was a very beautiful and elegant instrument. When that completed its operations, our final result from that was about 10,000 times more sensitive than Zeppelin 1. We are making great progress at rapid speed in our searches. We think we are now very close to the sensitivity required to see dark matter. Hopefully LZ will get there. LUX has also ended up in a museum. This is now at the Home State Visitor Centre. You can go there and see it, and it's got a really nice display with a cutout on the front, and you can learn about how the technology works inside. So ending this history, we're now at the present. LUX-ZEPLIN, here's a picture of it just as it was being deployed. This is inside the water tank. We'll see that later, I'm sure. And there's 2 questions for LUX-ZEPLIN. Critically, how sensitive will it be? Will it be sensitive enough to finally see this dark matter? And when it finishes, I'd like to know which museum it's going to end up being an exhibit in. Thank you, Sophie. Back to you.
Fantastic. Thank you so much, Alex. That was a fascinating trip around through the history of dark matter detectors. And I think it really gave me, at least, an idea of just how far we have come, how quickly things are changing in this field. So I've been seeing that there have been some really amazing questions coming in through the Q&A. I can't wait to ask some of them. Those of you watching on Facebook, please do pop some questions in the comments for us, or use the hashtag AskDarkMatterDay. Right. The next part of our talk, for the next part of this event, we're going to take you on a virtual tour around one of my favorite places, in the world, the Boulby Underground Laboratory. And we are going to be joined by Chris Toff, Ed Danks, and with help from Maria Wood as well to give you a quick trip around the lab. So Chris first heard about the Boulby Underground Laboratory at school, and a few short years later, he was working there. He actually started as a volunteer looking at background radon levels, then worked as a technician on dark matter experiments before accepting a permanent role at Boulby, working not only on dark matter detection, but also a whole host of other experiments. He's also an avid mountain biker and is proud to have only broken 2 bones whilst riding, which doesn't seem great, but better than 3, I suppose. He's going to be joined by Ed, who after doing physics at university, Ed spent some time as a software engineer before returning to science to work at Boulby. Ed looks after a range of different experiments working with scientists from around the world on areas from the hunt for dark matter to terrestrial biology and astrobiology. He's also Boulby's resident expert in board games. Behind the scenes, Chris and Ed are joined by Maria, who is local to the Boulby area and has just started working at Boulby this month on the underground facility support team. So I hope you enjoy this tour of Boulby. I'm sure you will. We're going to hand over to Chris to get the tour started. Over to you, Chris.
Hello, thanks, Sophie. I hope you can all hear me. Welcome. You are now in Boulby Underground Laboratory. We're in the northeast of England, just north of Whitby. If you ever come and visit us, please try our fish and chips. They're some of the best in the world. But where we are right here is 1.1 kilometers underground. You wouldn't know it. We're in a lovely clean space. I'm in a nice clean outfit. And this is where we do our low background science. As you've heard in previous talks, we come down here to get away from all that background radiation. So a lot of the science that you see behind me that I would love to spend all day talking to you about is all about getting away from background radiation and exploiting the environment that we're in. But today is Dark Matter Day, and so dark matter is the star of the show. So I'm going to leave this all for another time. Please check out all of our science. But today we want to talk about dark matter. Now, Alex gave a really good talk about the summary of the UK dark matter contributions and some pictures, and we have the real thing. So as Alex was saying, Zeppelin is a rich part of Boulby's dark matter history. The Zeppelin 1 program was the foundation. Zeppelins 2 and 3 really laid the way for dual phase technology, the technology that's now widely used around the world by some of the best dark matter detectors and setting the best limits. And so we're very proud to have our, albeit Alex called it coffee table, cryostat from Zeppelin 2. And to add to it, he also mentioned a few PMTs. If you don't know what PMT is, this is what a PMT looks like. It's a lovely glass bulb affair with a vacuum inside. And the way to think about PMT is it's like a reverse light bulb. With a light bulb, you put electricity in and light comes out, as you can see above us. With a PMT, you put light into it and electricity comes out, and you can then read that as a signal by your computer. But enough of the past, we want to know what's going on right now. So if I come this way, also huge shout out to Maria, who's behind the camera. Thank you very much, Maria. This is one of 2 current dark matter detectors that we have here in Boulby. This is called NEWS-G. And the actual detector part is this beautiful spherical vessel that you can see here. And NEWS-G is hoping to exploit this design to be able to probe into the low mass region of our dark matter parameter space. Now, I'm not going to go too much into the detail about dark matter, but there are many, many candidates that could be dark matter. Some of them are very heavy, some of them are very light. And depending on how you build your detector, makes it better or worse at finding different types of dark matter. So this particular setup will be one of the better setups for low mass region searches. And this is only a prototype. Eventually, this sphere is going to grow to a 3-meter diameter sphere, so a rather large affair. And when that's constructed and deployed, that will be the best dark matter searcher in the low mass region, we hope. The other cool thing about NEWS-G is that it hopes to exploit directionality in the future with use of something called an Akinos probe. So in this detector, there's a very special cathode, and depending on how you build that cathode, as Alex mentioned again, you might be able to figure out not just that you've seen a particle, but where that particle came from in the universe. And that's a really useful tool. So that's hopefully for the future. But on the theme of directionality, let's go on to Cygnus, or as it used to be called, Drift. It's since joined the Cygnus collaboration. And this behemoth of white behind me is the very detector itself. Drift is, or was, one of the best directional dark matter detectors in the world, setting some of the best directional limits at the time. At the moment, it's now being used as an R&D project as the wider Cygnus collaboration behind me. but ultimately it tries to exploit that trait of directionality to be able to not only find a dark matter particle, but then tell you where it comes from in the universe. And that sounds like a strange thing to want to know, but it gives you a clue into the WIMP wind, something that may be described later or you can ask questions about. But this will give us a really good discrimination against the background that we sometimes see that we try to get away from by coming down here in the first place. So we have all sorts of good things down here. This drift's even been signed by a Nobel Prize winner, Kajita Sensei, which we're very proud of. But I've shown you all the wonderful high-tech stuff. You can see all the cables and clean things behind me. I'm now going to hand over to Ed, who's in the complete opposite end of the spectrum, from clean room to Ed. So over to you, Ed.
Thanks very much, Chris. That's perfectly timed tannoy going off, which proves, I think, beyond doubt that we are in a working mine. So I was going to say, so far, what Chris has been saying and showing you, it looks very much like a lab that could be anywhere, whereas now I am stood in the tunnels of the mine. So I'll turn my camera around. Hopefully you can get a good look. So they're not necessarily what you'd expect from mine tunnels. They're about 3 or so meters high and about 8 meters wide. So there's enough room to walk around in them without being claustrophobic. And as you've heard quite a few times, the rock above our heads is a fantastic way to absorb loads of cosmic rays. So for approximately every 1,000,000 cosmic ray events that hit the surface, we only get one down here where we are in Boulby, which is 1.1 kilometers underground. So this is fantastic for dark matter because our detectors need to be really sensitive. And if you've got all that noise on the surface, it just sets them off and they go crazy. So we are underground. Like I said, it's an active mine. They're currently mining for polyhalite, which is a type of rock salt. The mine opened about 50 years ago, mining for potash, also a type of rock salt. And this is used as a fertilizer. So it gets shipped all over the world just to help crops grow. So all of this salt was left behind about 230 million years ago when a sea called the Zechstein Sea evaporated. So this was a sea that covered a lot of the area that's now the North Sea, parts of North Germany and Poland, and parts of the Northeast UK as well. So over time, as it evaporated, the salt got left behind. And then over millions and millions of years, that got compacted down into really the salt tunnels that we see around us now. So where the mine workings actually are is not close to the laboratory. They're over 10 kilometers away because the tunnels extend way out under the North Sea. Where we are, we're only about a 10-minute walk from the lift. The miners actually have vans underground and they get in the vans and drive to wherever they're mining. For us, it's just a bit of a walk through the very dark tunnels. We don't have lighting in most of the mine. It's a very strange place to work. I saw a question in the chat that says, is it hot underground? It absolutely is. Fortunately, in the laboratory building, we have air conditioning, so it's not too bad. But if you are working outside in the tunnels, it can be 10 degrees or more hotter than it is on the surface. This is simply because you're closer to the core of the Earth, and you've got all that extra heat coming off the rock. So our location underground does let us do a couple of other experiments in addition to dark matter. Just super quickly, we use our tunnels outside to test Mars rovers. So we have people from NASA and from the European Space Agency and all over the world. They come here to Boulby to test technology that's going to be sent on rovers to Mars and other planets. We can also use the rock to test whether it's suitable for large-scale energy storage, which is going to be very important as the UK moves to more and more renewable energy sources. So in addition to shielding us from extra radiation, from cosmic rays, there's other sources of radiation that we need to be aware of. And one of those is radon. So radon is a naturally occurring gas, and it's heavier than air, and it emits radiation, hence the name. Because it's heavier than air, this is a big problem for a lot of mines, because it sinks below normal air. And if you've got a mine shaft, it's all going to sink to the bottom of that as well. So we're very fortunate here at Boulby that we have a very low natural radon level. And this is particularly important when we want to be testing for incredibly, incredibly low levels of radiation, which is something that we do in our facility bugs. And I'm going to hand you back over to Chris now, who's going to tell you all about our bugs facility.
Thanks very much, Ed. Hopefully you're joining me back in the bugs facility. You've gone from one extreme to the complete other. Where Ed is, it's very dirty, it's very salty, it's dust everywhere. Where we are right now, I've had to, you may spot, I've got gloves on, I've got a hairnet on, different colored hat. I've had to get quickly changed so I can bring you into the BUGS facility. So BUGS stands for the Boulby Underground Germanium Screening Facility. So that facility requires a really, really clean space, and that's where we are. We were in a clean room to begin with. We've now gone an extra layer of cleanliness on top of that, and that's to house these very delicate detectors called germanium detectors. So what does this have to do with dark matter? Well, you may not realize, but everything around you is even the smallest things is a slightly bit radioactive. Dust even is radioactive. And so when you come to build something like a dark matter detector, you need to know exactly how radioactive your dark matter detector is. If the parts that you've built your dark matter detector out of are really radioactive, it's useless. You can bring them down to a nice low background area like we are in Boulby, but you will just be detecting your own detector, and you'll know it's there because you've built the thing. So instead, what you should do is you should make use of something called material screening. Now, material screening is where you identify parts, components, or even just materials themselves that are either intrinsically or have been made to be specifically low background. So it could be anything from a resistor to a sheet of copper that you're using as part of your shield to the entire vessel of your detector. What you do is you select small parts of materials or the actual components themselves, and you place them in these germanium detectors that you see behind me. These germanium detectors are incredibly good at finding the faintest amounts of radiation. And so these will detect almost entirely all the radiation that those bits of components or fuses or whatever emit. And so when you come to building your dark matter detector, you can do a couple of things. You can either be happy with the components that you've chosen, and you simply understand the contribution of radiation that they give to your detector, and you subtract that from your signal to make your backgrounds better. Or what you could do is say, nope, that resistor is too radioactive, I need a better one, go back to the company, and you can work with them to develop better systems, better components for your detector. So that's one use. It's a way of improving your simulation or even improving your detector itself. And though this is critical for dark matter searches, because dark matter particles, as we're increasingly learning as time goes on, seem to be more and more sensitive, more difficult and weakly interacting particles. And so we need the very, very quietest detectors, radioactively speaking, in order to be able to detect them. Now, there's a couple of other uses that you can use with these germanium detectors, things like leads dating, so like carbon dating. You can do it with lead because these detectors are so sensitive, or you can do a whole host of weird geological things that I'm not going to tell you about today. But just understand that these are incredibly good detectors at understanding very small amounts of radiation. Now, these use the technique of gamma spectroscopy. So they're looking for gammas that are emitted from those materials. But of course, radiation comes in all different types. So whereas these detectors will tell you how radioactive a material is intrinsically, sometimes you may want to know about the amount of radiation on a material. And so for that reason, we have something called an alpha counter in the corner. This surface alpha count here, it's a lovely, very nice white box. And that machine is slightly different to these germanium detectors in that instead of looking for gammas emitted, it looks for alpha particles. And alpha particles are a really good indicator of radon deposition. Now, radon, to a particle physicist, is the bane of their lives. It gets everywhere. It drops radioactive materials out from the air, and then those radioactive materials then emit radiation into your signal. It's a pain. So by understanding how much radon and radon deposition you get from a detector like the XIA alpha counter, you can have a better understanding, not just about the intrinsic radiation, but of the surface radiation as well. And the surface radiation is going to become more and more important as time moves on, as we go into the third generation of dark matter detectors and beyond. Because as these detectors need to become more sensitive and sensitive, they need to get larger, bigger vats of liquid xenon, for example. And with larger detectors, you get larger surface areas. And so knowing the surface area contribution of radiation becomes all the more important for future dark matter detectors. And it's also not only for dark matter detectors, things like neutrinoless double beta decay event searches, or even neutrino searches, all depend on these incredibly low radiation detectors, and so really high precision material screening in order to function correctly. I think that's all I've got time for, I'm afraid. I'd love to tell you about all the other science that we do here, but we're just not time. Maybe another time, if you could check out our YouTube channels and other social media, maybe you could learn more, and we hope to see you soon. And if you come and visit, make sure you try our fish and chips. They're really, really worth the wait. So with that, back to you, Sophie, and enjoy the rest of Dark Matter Day.
Fantastic. Thank you so much, Chris. And thank you, Ed, Thank you, Maria, for an amazing tour of the Boulby Underground Lab. And as Chris said, the chips they are really excellent. We promise. Do try them out. I'm just having a look at the questions. We've got some amazing ones coming in. Do keep them coming. We will answer as many as we can throughout the panel session at the end. So you can either use the Q&A button or put comments into Facebook or use the Twitter hashtag AskDarkMatterDay. All right, we're now going to have a virtual tour of the Sanford lab, and because we're going to start up on the surface, go down in the cage, and then into the cavern and see all of the experiments themselves. So we're going to take you on a 3D virtual tour of the Sanford lab. So this is also available on YouTube, so you'll be able to slow it down and watch it later as well, if you would like to see all of those little details. So the team over at SURF, are you able to play our video? Fantastic. Sorry, for one, sorry, team at SURF, I think that I'm having a few difficulties hearing sound. Would you be able to pause it? I think you might have to reshare with your sound screen, with sharing your sound. I think another couple of people are having the same issue. Sorry about this, everybody. We may work a mile underground and deal with some of the most exciting technology in there, but we have the same problems with Windows as everybody does. Okay, I'm not sure I can hear sound either. I think if you stop sharing and then reshare, making sure that you tick the box saying share sound. Bear with us for just 1 minute. Like I said, Zoom is just as new to us as it is to everybody else.
My name is Jared Heiss. I'm the science director, and I'll be your host for today's quick virtual Neutrino Day tour of the underground lab called the Davis campus. Our first order of business is to make sure that we brass in on the tag board. Mission accomplished. Now that the cage has arrived, our chariot awaits. Who wants to go underground? I'll meet you down there. Every morning when the researchers come underground, they gather at this area and talk through the events of the day. This is a coordination board. You can see lots of different groups that are underground today. Should be an exciting visit. Quick point of interest before we make our way to the entrance to the Davis campus. We're standing at the junction between the past and our present. Behind these doors was a rock face back in the fall of 2009. Since then, we've excavated 17,000 tons of rock to make another approach into the Davis campus and provide new lab space. Off to my left is the way that Ray Davis walked to work starting in the mid-1960s. Ray was a pioneer in the field of underground science. He was looking for neutrinos coming from our sun in a huge vat, 100,000 gallons of dry cleaning fluid. He was looking for the transformation of a chlorine atom into an argon atom once every 2 days for almost 30 years. That's a hard way to make a living. Follow me. We're going to go into the Davis campus. Hello, Robin. Our tour is with us. We're ready to come in. A couple quick things that are points of interest here at the entrance. We have our wall drug sign For those of you who are familiar with the South Dakota landscape, that's a required portion. This one has a vertical component that most don't. The other feature here, before we go in, just to quickly point out, we have a world map that shows where different researchers who work in the Davis campus are from, both where they're born and what institution they come from. And one interesting feature on top of that is the fact that we have the moon represented. We had a visit from Buzz Aldrin a few years back, so he's represented here as well. Let me complete the introduction. Robin Barlin is one of our laboratory custodians, and she's going to help us transition from the dirty, which isn't so dirty, into the clean. Well, welcome to the Davis campus. We are on the clean side now, having come through the cart wash. Just a quick review of why we're underground. This group looks pretty adventurous, so they may have hopped on an elevator at the drop of a hat in any case, but there's a reason that we come underground. And that is because for the physics experiments that are looking for very rare processes, they would be swamped by cosmic rays on the surface of the Earth. If you hold out your hand where you're at, chances are you're getting about 3 cosmic rays per second going through your hand. Coming underground about a mile reduces that by a factor of almost 10 million. So what does that mean? On the surface, 3 per second. Here at the Davis campus, it's more like 1 per month. And if you're looking for a very rare process that no one's ever seen before, you want to give yourself every advantage. And that's exactly why the physics experiments that we'll be talking about today, the Majorana demonstrator, studying properties of neutrinos, and the LUX-ZEPLIN experiment, looking for dark matter. So let's just say a few words about those mysteries. Why are they important to understand? If we look out into the cosmos, studying the matter and the energy that we see around us, only 4% of the matter is known. So tables, chairs, stars, planets, galaxies, that's 4%. That's hardly anything. That means 96% is unknown. And that's the part that we're really interested in. A lot of that is in dark matter. About a quarter of the matter energy is in dark matter. And then beyond that, there's dark energy, which we're not going to talk about today. But there's so many mysteries. It's an exciting time to be a scientist. The universe is a more interesting place than we ever imagined. Behind me is the Majorana demonstrator machine shop. $750,000 worth of tools are used to work on some ultra pure materials that are used to fabricate the experiment. In particular, the Majorana demonstrator collaboration produces the world's purest copper. You may have heard the term parts per million, parts per billion, parts per trillion. Their copper is 10 to 20 parts per quadrillion. That's an amazingly pure substance. And they use that in the housing and some of the connectors that go into connecting the germanium crystals into strings, and those strings are then put into a large cryostat. That cryostat is also made of electroformed copper. So how do they get that copper? Well, first they grow it in a set of acid baths. You start with the purest copper you can buy commercially, oxygen-free, high conductivity copper. Immerse that in ultra-pure acids, create an electrolyte. Add a stainless steel cylinder, in this case maybe roughly a foot in diameter, 18 inches long. And over time, with a voltage applied to this metal cylinder, you can plate out the atoms, the copper atoms, capital ions, to form a skin. It's a very slow process, roughly 1 millimeter per month. So to get a ½ inch thickness on the outside of that cylinder, you have to wait about a year. That's a slower growth rate than your fingernails. So you gotta be very patient. Let's turn our attention back into the detector room. It's a little hard to see, but back in that far corner is where the almost 50 kilograms of germanium is situated. It's protected from the natural radioactivity that's all around us. It's around you, even in an underground lab like the one I'm in. There's natural radiation from the spray-on concrete, called shotcrete, from the ducts, from the pipes, from the floor, from the people. And in order to protect the experiment and increase the chances of seeing these rare processes, they generate or they build a large shield And you can see the start of it in some of the pictures on the poster. The inner part is copper, both commercial copper and that electroformed copper. Almost over 4,000 lead bricks surround that, almost 60 tons or over 60 tons. And then around all of that is a lot of plastic, polyethylene, to make up the shield for neutrons. So different shielding components for different radioactive backgrounds. All told, the Majorana shield is over 70 tons. That's larger than a 757 jumbo jet, a mile underground, parked in the corner of that room. Pretty impressive. Well, welcome to the Davis Cavern. This is both hallowed and hollowed ground. Hallowed because this is where Ray Davis did his work starting in the 1960s. We talked about that a little bit already with the large tank, 100,000 gallons worth of dry cleaning fluid, looking for neutrinos coming from the sun. And it's hollowed because it's a cavern. We've done a little bit of redecorating in the time that since Ray Davis has used it. We've made it a little taller, a little wider, and there's been now, this is the second dark matter experiment that is being installed in this location. Previously, the LUX experiment started taking data in 2013. They wrapped up, moved out in 2017, and now we're moving in the next generation, the LUX-ZEPLIN experiment that will use 10 tons of xenon to look for possibility of a weakly interacting massive particle or a dark matter particle. Let's go take a look and see inside the water shielding tank for LZ. Well, there's not a lot of room here, but I want everyone to gather around so we can take a look inside the water shielding tank for the LZ experiment. We're in for a rare treat today. Sometimes in recent days the lid has been covered, but the lid has been retracted so we can actually see inside the water tank. The LZ detector is in the center of the space below, and then around on the perimeter of the tank are some outer detectors that will help detect neutrons that are coming into the space. So we talked a little bit about shielding with the Majorana demonstrator experiment, the large amount of lead, also copper and polyethylene. This experiment uses something slightly different. It uses a water tank filled with ultra pure water, up to 72,000 gallons. So what's going on with the LZ experiment? As I mentioned, they're using xenon, 10 tons of xenon, to look for interactions with weakly interacting massive particles that we think populate our universe, interact with the xenon to produce bursts of light. And the LZ experiment looks for 2 bursts of light that help tell what type of particle it is, be able to tell a dark matter particle from a normal particle that we might be very familiar with already, like a neutron, like a gamma ray, like a beta particle. So purity is very important. The LZ experiment was assembled on the surface, just like its predecessor, the LUX experiment. It was brought down in the cage that we rode down in today. In fact, the LZ detector was so large, it had to be lowered underneath the cage. It was too big to fit inside the elevator where we were. It was brought into this space and lowered into this tank. Later this summer, the tank will be filled with water and their production data run will commence. Let's take a look down at the lower level and see some of the other supporting systems that enable the LUX-ZEPLIN experiment to look for dark matter. Follow me. Here we are on the lower level of the Davis Cavern, and this gives us a better opportunity to see how big that water shielding tank is. 25 feet tall, 20 feet in diameter, and as I mentioned previously, 72,000 gallons of ultra-purified water. The water purification plant, incidentally, is through those gray doors in a plant on the dirty side of the laboratory. What you see around us right now are a lot of the parts and pieces and systems for purifying the xenon that will go into the LZ detector. This is the xenon tower. It is a heat exchanger of sorts. Takes the liquid xenon from the detector, turns it into a gas. The gas gets purified, reliquefied and reintroduced back into the detector. There are some other test parts here that are used to commission the system. Those will eventually go away. But as you can see, and as we saw above, not a lot of room for a lot more equipment. They've done a really good job of stuffing this place chock full with scientific equipment. We'll take a look around the tank at a couple of points of interest before we wrap up our tour here at the Davis campus. We've seen the water tank from up front. We're going to do a quick walk around, show you the tank in all its glory. We're going to walk the perimeter here. We're not going to go into the water tank, but here's the entry port for those workers who gown up in clean room garb. They can go inside the water tank and work on all the detector components, on the outer detector components, those acrylic tanks, and other systems that are in place there. This plastic tent that you see separates the main space and just gives a bit more higher level of cleanliness for going into the water tank. We don't want any of the contaminants from the lab getting into the water tank and contributing to backgrounds for the experiment. Well, that wraps up our tour of the Davis campus. I was really thrilled to be able to show you all the cool things we're doing underground here at Sanford Lab. So thanks for joining me, and I hope that this virtual tour was enjoyable. Have fun at Neutrino Day, virtual or otherwise, and I gotta catch my cage, so I'll see you next time. Bye-bye.
Thank you so much, Jared, and the rest of the team over at SEF. That was absolutely fascinating. I'm sure you all enjoyed it as much as I did, and now want to visit as much as I did, as I do as well. Do keep the questions coming in. We're getting some brilliant ones from Zoom and from Facebook. We're actually answering some of them via text so that you can, so that we can get to more of them throughout this event. So do check out the questions and answers that you can see that have been answered via text. Now we've got our final short talk where we'll hear a bit about the future, what LUX-ZEPLIN could accomplish when it's turned on, and how the search for dark matter may look over the next few years. And we've got Sally Shaw coming to tell us about that. Sally is a postdoctoral researcher and professional dark matter hunter working at UC Santa Barbara. She's originally from Nottingham in the UK, and she completed her PhD in particle physics at the University College London in 2016, before moving out to California to continue working on the currently under construction, as you just saw, LZ dark matter detector. She's often found wearing a hard hat and coveralls 1 mile beneath the surface at Sanford Lab in South Dakota, and her work mainly focuses on ensuring any signal seen by LZ is really a never seen before dark matter particle and not a fake. So a very, very important job. Thank you very much, Sally. Over to you.
Okay, thank you, Sophie. So I'll just share my slides here. Okay. So you should be able to see my slides. So hi, everyone. So I'm going to be talking about the future of dark matter direct detection. You already heard about the past from Alex. So first of all, let's just talk about the next 2 major searches for dark matter that are sort of underway and beginning really soon. So you've already heard lots about LZ, which is LUX-ZEPLIN. It's located in Leeds, South Dakota. You just had a nice tour of Sanford Lab where LZ is located. And we actually, I work on LZ, so that's what I'll be focusing on today. But it's also, have to mention, of course, we have a rival of sorts, which is the Xenon N-ton experiment over in Gran Sasso in Italy. And they're actually located rather deep underground. They're actually under a mountain. So for the same reasons of shielding cosmic rays. And LZ is actually slightly bigger than xenon n-ton, contains 10 total tons of xenon, whereas xenon n-ton is 8, the n is 8 tons. So, you know, we do have slightly more xenon, but they are sort of our competitors in the search for dark matter. So of course, there are two possible futures for these two experiments that will be both sort of beginning their searches for dark matter really soon. Number one is, of course, what we all want to see is that they both see a convincing dark matter signal, and it's sort of the same signal. And that would be huge. We would be very, very happy. We would be celebrating. Nobel Prizes would be awarded. And it's really important that when we do see a dark matter signal, we will want to confirm it by using results from other experiments. So that this would be very exciting if both of these experiments saw the same signal. Additionally, you know, they might both see no signal, which is unfortunate, and we'll be banging our heads against the chalkboard here, as this picture shows. That'll be very disappointing for us, but it also won't be entirely surprising, as that's happened to us before with the previous experiments. There is, of course, a scenario where they both, actually one of them sees a signal and the other one doesn't. That would be very, very confusing, and we'd have to put a lot of work in to understand what was happening there. Okay, so I'm going to talk a little more about LZ, because of course this is the experiment I work on. You already saw some really nice images of LZ as it's undergoing construction. It is a big, big tub of liquid xenon of, you know, those 10 tons in there total. So that is contained in the middle of a titanium cryostat that sits inside a big water tank that you actually saw inside on that video just now. And you see that it's sort of like a Russian doll configuration. There are layers to this detector, and that's all about keeping it kind of screened and shielded from background radiation that can mimic dark matter. So these green and blue tanks in particular, these are made of acrylic, and they're filled with a special liquid that is able to detect neutrons. And that helps us a lot because neutrons can actually look just like a dark matter particle when they interact in the liquid xenon. And then we have water all around everything, you know, shielding us from the walls of the cavern itself, which are also radioactive and are constantly spitting out high energy photons called gamma rays into the detector. So it's all about shielding, going underground, the water tank, everything. It's all about keeping LZ in the most sort of quiet and least radioactive environment possible to give us the best chance of seeing these really rare dark matter interactions. So here's some photos of LZ under construction. You know, it's pretty photogenic looking detector. So, you know, you can see all of these. You've probably seen these on social media before. You'll see that on the top left, that's me standing amongst the acrylic tanks that will be used to detect neutrons. You can see the titanium cryostats we talked about that hold the liquid xenon and keep it cold. At the bottom there is, this is the sort of main heart of the detector called the time projection chamber, and that will that contains liquid xenon. And the reason it's so bright and white is that allows us to collect the most light, because this is how we actually look for dark matter, is we look for it interacting with xenon and producing light that we then detect with these detectors that you see at the top right, which is these are called photomultiplier tubes, and they're basically the eyes of the detector that detect light for us. So here's our collaboration. This was the start of 2020. It feels like a lot longer ago, let me tell you that. There are about 250 of us across the world. You'll see, you know, we'll all be working very, very hard over the next year or so to produce sort of first dark matter results from LZ. This, I just wanted to show you the difference between our January collaboration photo and our July collaboration photo. And you obviously all know the reasons for this. We had to do it over Zoom, but we are already a global collaboration, and we're very, very used to working remotely with colleagues across the world anyway. So, okay, so what's next if we do discover dark matter with LZ and xenon and ton? Well, we'll need to study the dark matter particle. We want to know things like how heavy it is, how it actually interacts through what sort of physics processes. Is it one particle or is it lots of particles, you know, all together? And it also, what we'll really, really want to do is know if it can help us understand other big problems in physics. So, you know, I think a couple of these are mentioned already. Dark energy was mentioned. These are the sort of the big problems and mysteries in physics right now, are things such as, why are we all made of matter and not antimatter when they should have been produced in the same quantities at the start of the universe, and they actually should have sort of cancelled each other out and annihilated and just produced pure energy. But instead, we're all made of matter, and we don't see much antimatter, and we don't understand why. Dark energy is this mysterious substance that makes up sort of 70% of the universe, and it's accelerating the expansion of the universe. But again, we don't understand what it is. And quantum gravity as well is about unifying sort of Einstein's theory of general relativity with sort of particle physics, like small scale stuff. And that, again, is something we've not been able to do yet. And hopefully what we're really hoping is that by discovering that missing sort of 27% of the universe that is dark matter, we'll open some windows and get some light on these other mysteries that we're still trying to solve. So what if we don't detect dark matter? Of course, this one's really easy because we've done it multiple times before. All the experiments you heard about in Alex's talk have not been able to detect any dark matter. So what we actually do is we set constraints on the dark matter properties, which means like we rule out certain types of dark matter so we can focus our search, our search elsewhere. So we draw these fancy looking plots or graphs that show, they have the main thing to know is that we basically put on the x-axis the size, the mass of the dark matter particle, and on the y-axis is its probability of interacting in our detector. And as you go down, you're actually, making the interaction rarer and rarer. So when we draw the lines, when we finish the dark matter experiment, we don't see anything, we draw a line, and above the line, we've ruled out all of that type of dark matter, but below the line is still fair game. Our detector was not sensitive enough to detect any dark matter that lives down there. So the idea is to keep trying to build new experiments that push that line further and further down or across. So you'll notice, for example, we actually are not very sensitive to very, very light dark matter particles. So I wanted to show, just give you a bit of a laugh, some of the headlines that we receive when we don't detect dark matter. They're not very positive. They say that we failed, we can't find any invisible dark matter. We came up empty-handed. And of course, although one should never, ever look at the comments section, if you do, you'll see people complaining like this, saying they're very skeptical of scientists, asking for money to build a bigger one because they think we look at blank screens all the time. Well, I can tell you there's no looking at blank screen involved. These detectors see a lot of stuff all the time, even when they're not seeing dark matter, they're seeing all kinds of other physics. And there's lots of interesting things we can do that actually aren't dark matter. But I underline here, build a bigger one, because actually this is the plan, of course, is we've done it before and we want to do it again. We want to build a bigger detector no matter what the results of LZ are. So if LZ does see dark matter, it'll probably only see a handful of events, a handful of particles. And we'll want to build a bigger detector so we can see more of them and really study dark matter. And if LZ is not sensitive enough to see dark matter, we'll also want to build a bigger one to have another go at it. And I tried to show in this sort of cartoony way here why we want to build bigger detectors all the time. And the reason is quite simple. It's just a bigger target gives you a bigger chance of seeing a dark matter particle. Because as the Earth moves around the galaxy, we're actually sort of passing through a big sort of what we think is a big spherical distribution of dark matter. So we think that dark matter exists in a big halo around the galaxy at a sort of certain density. So there are the same amount of dark matter particles just sort of sitting, passing through us all the time as the Earth moves. And, just having a bigger target means you snag more of those dark matter particles in it. As you can see, the little LUX detector here only gets a couple, LZ gets a few more, and a much bigger detector sees many more. So that's why we keep trying to build bigger ones. So as we wrap up here, I'm gonna just show you this another plot. I tried to avoid showing too many graphs, but the point of this is just to show these are all different dark matter experiments. You can see the year on the x-axis there. We've been doing this since the 1980s, and we have plans to do it until at least 2030. So you'll see at the bottom right, you can see LZ and xenon n-ton, where they're sort of projected to end up. This is getting more and more sensitive to dark matter as you go down. And Argo and Darwin at the bottom right there are like much, much bigger. We're talking 50 to 100 tons of liquid xenon or argon there. And that would be our what we call a dark matter observatory, where we're really hoping either to be able to study dark matter more or finally detect it if we don't manage it with LZ. But this has been a long slug. This has been going on now for many, many years, and we're really, really excited about the next generation of dark matter experiments, as we may finally see something. But if we don't see what we're expecting to see, which is WIMPs, which are the most likely candidate for dark matter. These are weakly interacting massive particles. If we don't see any of these, there are plenty of other mysterious candidates for dark matter, like other types of theorized particles that it could be. And that, these will require different methods of detection, different types of detector, different technology. So the plan is, if we don't see anything by the time we've built these big experiments in 2030, we'll start to focus efforts on elsewhere and then try different technology. It's always nice when you work on these searches. Sometimes it's a little disheartening to always be finding nothing. But as apparently Albert Einstein would said, that the pursuit of knowledge is more valuable than its possession. So it's something to keep in mind. We're just going to keep pursuing that knowledge for as long as we can. Okay, thank you.
Fantastic. Thank you so much, Sally. That was amazing. And I am sure that everybody is just as excited as you and I am. It seems like we're in for a really interesting few years. So thank you all. Thank you to all of our speakers. I'm sure if we were in a big lecture theatre all together, you would be getting amazing rounds of applause right now. So you can hear me applauding, but we'll now move over to our panel discussion. We've had some amazing questions in through Facebook, through Zoom, through Twitter. So I will be joined by some of our previous speakers. So Jarrett's going to be joining us from Surf. Alex will be joining us from Edinburgh. Ed will be joining us from down in the mine. He's still out in our Marja down in Boulby, and Sally will be joining us as well. So if we can get the panel up, I'll just bring everybody in, then I can start to ask you all some questions. Brilliant. So we've had some amazing questions, and panelists, if you're having a look at them and would like to answer any in particular, just give me a wave and we'll go to one of those. But the first question that I was going to ask to anyone is, how do we know that all the shielding and being so far underground will not block out dark matter? And will neutrinos still get into the underground laboratories? That's from Brian, but we've got another few questions that are fairly similar to that from other people as well. So who would like to take that? Don't all shout at once. Alex.
Okay, so certainly neutrinos do still get down to us. At some point, we will be limited in our sensitivity by neutrinos. There are many neutrinos coming out of the sun, but when they scatter in our detectors, they leave a small enough signal that it's not a problem at the moment. But as we get more and more sensitive, that background from neutrinos will become an issue. As for how do we know that dark matter isn't going to get shielded by all the shielding we're putting in place, I think it's because the properties of dark matter that we need to, when you look at the universe and we look at how stars are moving around in galaxies and how galaxies are moving around each other, and just how the distribution of stars and galaxies lie in the universe, we can try and model that in cosmology and astrophysics. And you need to include dark matter with a particular set of properties to recreate a universe which looks like that. And so those properties tell us that it's not going to interact with the materials around us.
Fantastic. Anybody have any other points to add to that question? Any of our speakers? No? Jarrett? Oh, Jarrett, I'm not sure we can. Perfect. Sorry, we couldn't hear you. Would you mind repeating that, please, Jarrett?
Oh, I was just going to add, follow on to what Alex was saying, that that if dark matter was subject to the forces that would allow it to interact with normal matter, like the shielding we've discussed, then we would have seen it long ago. And so by virtue of the fact that we haven't seen it, it narrows down the types of interactions that it can participate in. And the shielding would not have any effect on gravitational or at most weakly interacting dark matter particles.
Thank you all. Moving on from that slightly, we've got a question from Olivia. Is there a possibility that we're looking for the wrong thing? What if dark matter was more similar to gravity, which acts more of a force that manipulates matter? Rather than trying to quantize it, could it be detected similarly to gravitational waves? Who wants to take that one?
I'm happy to say something again, but I'll allow someone else to have a go.
Alex, why don't you start us off and then...
Okay, so we don't know what dark matter is. It might be one of many, many things. And I'm not sure that anyone here would classify themselves as a theorist, but there are many clever theorists who come up with ideas for what it might be. And you've got to come up with an idea which would explain the observations that we see in astronomy, but is also consistent with not having detected it already. So there are solutions to gravity. So maybe all the evidence that we have for dark matter at the moment comes from gravitational effects, assuming that general relativity is correct. But perhaps general relativity is incorrect. However, it's been tested in many different environments and been found to be in excellent agreement with all the data so far. There was actually, the question mentioned gravitational waves, and there was a really significant observation recently where there was a neutron star merger leading to a gravitational wave event, but it also led to an optical observation, or gamma rays, being detected in satellites orbiting the Earth. And those gamma rays arrived at the same time as the gravitational wave signal, which is really important because that tells us that gravity travels at the speed of light. And many of the theories in which gravity was an explanation for the strange things that we see that we're inferring as dark matter, those theories would have predicted that gravity travels at a different speed to the speed of light. So that one observation instantly rules out many of those alternative modified gravity theories. There are still some modified gravity theories that could potentially explain some of what we're seeing, but those theories find it very difficult to explain all of the different observations that indicate that there's dark matter in the universe. But it's absolutely right. There may be, I mean, Sally mentioned axions, there's things like hidden photons, there's mirror dark matter, there's different modified types of neutrinos that could possibly be dark matter. So we rely at some level on guidance from theory, and that suggests still, I think, that the weakly interacting massive particle, perhaps generated by supersymmetry, but there are many other types of theory as well that generate these kind of generic class of weakly interacting massive particles. That's where we think the dark matter probably is.
Fantastic. Thank you, Alex. Do you have anything else to add, any of our other speakers?
Yeah, I think I could add something about, we find, you know, when very clever theorists look into this, they find that the amount of dark matter that we can observe through gravity in the universe is like sort of exactly what you would expect if the dark matter was indeed a particle that interacts through the weak force, or the weakly interacting, you know, force. So that's why we think that WIMPs are the best candidate. It just all the math works out. If that we had weakly interacting massive particles in the early universe, they would have sort of interacted with themselves and annihilated at just the right amount as the universe began to expand, to leave the sort of what we call the relic density, or just the right amount of dark matter that we observe today. So that the sort of the theory and the maths all lines up really nicely for WIMPs. That's one of the reasons we're like very convinced that it is a particle, and it interacts through the weak force, which is, you know, how we're trying to detect it.
Fab. Thank you, Sally. Anything else to add from anyone? No. Okay, I've got a little bit more of a practical question. How will the dark matter be identified with the equipment below ground? So I guess what will you see? Is it going to flash up on a screen? I don't think so, but how will it be identified?
Yes, I can start if that's okay. So the actual signal that we are looking for is called a nuclear recoil, and that is a sort of xenon atom it gets sort of, imagine the dark matter particle smacks into a xenon atom, leaving some energy in the detector. And what actually then happens is you get a sort of chain reaction of xenon atoms all sort of bumping into each other, and they actually become very energetic and emit light. So that's why we have these, you know, I showed a picture of the eyes of the detector that view the liquid xenon. So what we really look for, even though it's called dark matter, we actually look for light, so photons. And this, you know, it's the way we would be able to tell it was a WIMP rather than some other particle is, first of all, we want to make sure it interacted with the xenon nucleus and not an electron, because more common particles like photons and electrons will interact with other electrons rather than the xenon nucleus itself. And then we look for just one single interaction within the whole detector. So this is one of the reasons we have the layers of the detector and the outer detector, is to make sure that there wasn't more than one, this particle didn't hit more than once as it passed through LZ. And that's simply because one interaction of a dark matter particle is so rare that we don't expect it to happen more than once within its path through LZ. That would be basically impossible. So we can, you know, remove a lot of potential dark matter just by looking to see if it bounced more than once as it passed through LZ. And then, you know, like the more practical side of this is those light signals, they come out as sort of what we call waveforms, and they go through a whole data processing system. They're computerized, and they come out, and we actually, you know, run computer code over this to try and select sort of interactions that look potentially like dark matter. It's very complicated, so I won't go into too much detail, but there are things like we only select certain energy ranges, for example, where we expect the dark matter to see. But yeah, I'll stop there because otherwise I'll get too into it.
It's a lovely problem to have people who are so excited by the answers that they're giving. Would anybody else like to add to Sally's answer?
I'll just mention that. So Sally was explaining that we are looking for signals that are consistent with a sort of an expectation of how the light resulting from a scattering event from a dark matter particle. We've got an expectation for how that should look, and we look for something that's similar to that. And that's not just based on, oh, we think it should look like this. We can actually mimic dark matter particles quite well in the detector using neutrons. Now, neutrons are different because they scatter multiple times, as Sally said, but the way that they scatter actually looks very like what we think a weakly interacting massive particle would. So we can test that our apparatus is sensitive to signals that really do look like what we think a dark matter particle should generate. And I can also say, I mean, we don't just do this for the nuclear recoils. We're testing many different models all at the same time, some of which include scattering from electrons, some are including sort of more larger energy deposits that you might expect from a different class of dark matter particle, or lighter or smaller energy deposits that you expect from lighter particles, that kind of thing. So we're looking for a range of signals all at once, but essentially doing this by checking that there's many signals coming out from the detector, and we want to look at the combination of those and see if it's consistent with the distribution that we're expecting from a dark matter scattering.
Fantastic. Anything else to add, Ed or Jarrett?
I can just chime in briefly and echo what Sally and Alex have mentioned, but maybe put a finer point on it. The calibration program for these experiments, these detectors, is truly remarkable. You have to understand the behavior and response of your detector exquisitely. And successful experiments in this field really spend a lot of time, a lot of ingenuity developing calibration techniques. Neutrons have been mentioned a couple times, and so calibrations using neutrons, intentionally injecting neutrons of ideally low energies into your detector is not an easy thing to do. And these experiments have really refined their calibration programs, and it's absolutely required to get the results out that they're looking for. So kudos to these experiment groups that are really putting in a lot of effort here.
Absolutely, you're all amazing, I think. Fab, thank you. All right, we now have a question from some 6th graders in Ramona, South Dakota. Give them a wave, everyone. Why is dark matter called dark matter? How big are the lab campuses and how many people work at each campus? So who'd like to take, that's actually 3 questions snuck into one, isn't it? But who would like to be the first to answer that? Ed?
I'll jump in on that if that's okay. So it's called dark matter because of the properties that it has. It's dark because it doesn't interact with light. Quite literally, it has no interaction with the electromagnetic spectrum, and therefore we can't see it with the normal light that we see. But it still has mass because it still interacts with gravity. So it's still a type of matter, and that's where the name dark matter comes from. As for our facility, we're a relatively small team. We have about 10 people who work here. We have 4 scientists, 3 people on the facility side, and a facility director as well. You've seen some of our other scientists and facility people today. And hopefully Chris's video gave you a rough estimate of the size of the lab. But it's actually built within the existing mine tunnels that I'm standing in now. Apart from one section which was dug especially for us, that was dug in a direct north-south direction. Most of the tunnels are just kind of higgledy-piggledy. They were following where the salt was. And the machines that they use to create the tunnels, they create tunnels that are about, like I said, just over 3 meters tall and about 8 meters wide. So that's about the space that we had to play with when we were creating the fancy new lab as well.
Fab. Thank you, Ed. Anybody else want to share how many people work with you at your facilities? Who wants to go next?
I can chime in for Sanford Underground Research Facility. It's a great question. Number of personnel here at SURF, we have 175 people, but a lot of those folks are in our operations departments. So they maintain safe access underground. They are essentially the mining company. So Boulby is operated in an underground mine. We are a dedicated facility for science, so a little different, although we have a mining pedigree and legacy. So a lot of our personnel are employed in keeping the facility running and safe, operating the elevators, the cages up and down, making sure that those are maintained and are safe. The science department has 3 staff scientists plus myself, so a fairly small crew for managing just under 30 experiments. So we have to really reach into the organization, reach into those other 170 odd people to make science happen here at SURF. In terms of the sizes, you're looking at the Davis campus right now, one of the main laboratory spaces at the Davis campus. All in, there's probably 30,000 square feet. This would be a fraction of that. Dedicated to science, it's more like 10,000 square feet. We have another campus over at another one of our elevator shafts called the Ross campus. That is winding down in order to accommodate a really large experiment that's looking for properties of neutrinos. The long baseline neutrino facility. So there's a lot more space that'll be coming in our not too distant future. But for now, this campus, roughly 10,000 square feet. The Ross campus, roughly 10,000 square feet. And the LB&F campus will be 5 times that footprint and 25 times that volume of those 2 combined campuses. So a huge, huge addition to our facility coming soon. Great question.
Yeah, exciting. Sally?
I don't really have anything to add to that since I work at the Sanford lab usually.
Okay, fab. And Alex, you don't work at one of the facilities, but your university, I guess. How many people?
No, I think I'd just like to say that as a user for these facilities, I am awestruck by the professionalism and the dedication of the staff running these places. They look like Star Trek now, right? They are fantastic. That said, working underground is an intrinsically dangerous activity. So we counter that by taking extraordinary measures to keep ourselves safe and our students and postdocs and things. So all of this makes it a really exciting place to work. There's nothing quite like going underground. It's been compared to working in space. If you forget your screwdriver in the morning, that's it. You're not going to get another one for the rest of the day. It's an unusual environment, which makes it really exciting.
I agree with that, speaking as a visitor sometimes. Fantastic, thank you so much for all of those answers. So we've got a question from Facebook, from Jan. Are any people working underground on experiments during this pandemic, or are things on hold? So I think that we can see that a couple of you are underground, but over the course of the pandemic, how has that affected your operations? Who'd like to go first?
I can start, I guess. So here at SURF, we did curtail operations through much of April due to the pandemic. There were an increasing number of infections, but more logistically would be to make sure that our safety programs caught up to what we needed to be able to support science underground. And so we set up a health screening at our main entrances. We instituted requirements for personal protective equipment, PPE to come underground. We look a lot different than I look now. We wear masks when I'm not on camera, but to come down on the cage or the elevator, we wear a half-face respirator, we wear a face shield, in addition to other personal protective equipment like the safety glasses, like some other underground mining equipment, those types of hazards. So the COVID personal protective equipment and hazards are on top of that, layered on top of that. And we had to figure that out. A lot of experiments consist of institutions where personnel work, and those institutions have their own rules and concerns about traveling during the time of the pandemic. So as I mentioned, SURF was essentially essential personnel only, minimal operations for all of April. We opened up again in early May with all of these protocols in place. And slowly, some of the researchers were able to travel to SURF. A few key personnel were based here and stayed sort of hunkered down through April during that time of the pandemic, and were able to then come underground and assist with the experiment construction. But it was a challenging time. It did impact the schedule for some of these experiments that are in the phase of installing their experiment. Other experiments, like the one I mentioned on the virtual tour, the Myrana demonstrator experiment, they are basically in a mode where they're taking production data, and so you can collect the data off-site and don't need as many personnel underground to do the care and feeding for the experiment. There's some of that, but not to the level that the LZ crew that you see working hard behind me need to be on site to build their experiment up. So there's different experiments that are in different phases, and the pandemic affected them a little differently.
Thank you, Jarrett. Ed, do you want to answer for Boulby?
Yes, so a lot of what Jarrett said is very applicable to us as well. We shut down for almost 3 months with no access to the lab whatsoever, which was obviously a big challenge. We made as much of our stuff accessible remotely as possible, and everything that we couldn't do that, we had to shut down in a safe way. The big problem for us, and I'm sure for Jarrett as well, is just the lift. So the lift is not a normal lift that you get in an office building. It's a massive 3-story cage structure. They call it the cage. It's sort of metal with fabric flaps. It's not a solid building either. But in a normal operation sense, they have 60 people at a time in the lift, 25 and 25 and 10 on the various floors. And you're packed in a little bit like sardines with all the miners as well. So obviously that's just not tenable at all in a COVID world. So what they've eventually had to do is reduce the numbers. So now there's a maximum of 8 people on any floor of the lift, which obviously means that the number of people that can be underground at any time is drastically reduced. And we only have very specific times that we're allowed to come in and out the mine. Otherwise, we're just going to be stuck. So the big problem there is collaborating with the mine, working as closely as we can with them, and not disrupting their operations, and figuring out how we could slowly start to ramp our experiments back up when we just don't have that much time underground. So a lot of our experiments are slowly getting back towards normal, but it's definitely been a struggle.
Thank you. It's fantastic to hear that you've managed to carry on, but really interesting to hear about all of the different difficulties. I think you're doing an amazing job to be able to be doing it at all at the moment. So well done, everybody. So we've had a few questions around this next one, slightly different phrasing, but essentially, why do you use xenon in the detectors? Who would like to take that one? Anybody?
I'll take that again if you like.
Alex.
So xenon has several properties which make it a really good material for this. So the most important one is that when radiation strikes an atom of xenon, the xenon generates a little flash of light. And so that little flash of light gives us something that we can register in these photomultiplier tubes. So that's a scintillator. There are quite a few materials that scintillate, but xenon is really nice as well because we can purify it. It turns out the nature of it's a noble gas, element 54. You can purify it, and the biggest challenge we have, as I'm sure everyone's getting to grips with, are these background radiations. We're trying to find individual subatomic interactions in tons of material over periods of months. Whereas a human, you, me, each of us, we have about 5,000 gamma rays being emitted from us every second, just from the potassium that's in us. Everything is slightly radioactive. Xenon, we can purify it greatly, which makes it, which means that there's no radiation coming from the xenon itself. It's really that's really important. The xenon has a few other important properties as well that are more technical, but the overall, it just becomes if you look at all the different requirements that you have to make a good dark matter, a candidate material to see dark matter scatterings, it ticks all the boxes really well.
Fantastic. Thank you, Alex. Does anybody have anything to add to Alex's answer about why xenon is awesome?
I can quickly add one fun fact. Liquid xenon is as dense as the rock behind me. So 3 grams per cubic centimeter, which is hard to wrap your mind around, thinking of rock and a liquid being the same density. Xenon is quite far down on the periodic table, if you remember that. And so it offers very good shielding. The outer skin of xenon in the detectors that use that technology are able to provide an additional layer of dense shielding around the inner region, the quietest region, the most sensitive region for looking for dark matter particles in these experiments. So the fact that it's heavy and dense is also really important.
Fantastic. That is a cool fact. I'm going to steal that and use it. Brilliant. Okay, we've still got loads of amazing questions coming in, so I'm going to combine a few of them together. Is there any relationship between dark matter, antimatter, and dark energy? Who would like to take that one? Everyone always gets a bit scared, I've noticed, when we talk about dark energy.
Steal that one, because that's a great question. We don't know. Wouldn't it be great if there were? There are, we're at a real crisis, I think, at the moment in particle physics and astronomy. There are lots of things that really don't make sense. We've got more knowledge than ever before, and we've got fabulous technology, but there are fundamental things, like Sally was saying about, is that why are we made of matter and not antimatter? Why do we talk about neutrons and protons and quarks and electrons or whatever. They've all got properties. They've got a mass, they've got electric charges. Why do they have the values that they do? We don't know. This seems to have been just the way the universe works. Is there something deeper to it which explains why all of this happens? What is dark matter? What is dark energy? How does quantum mechanics work? How does gravity work? We know that gravity and quantum mechanics ultimately have to be slightly different models. The general relativity doesn't have a quantum description to it. So there's many different problems here, and of all of them, quite possibly dark matter is going to be the first that gets solved. And it would be really nice if in solving that problem, it kind of gives us a hint and a clue as to all of these other problems as well. Maybe there's something fundamental that we're missing about the way that the universe is working, and sorting out dark matter might well help sort out a lot of these other problems. There's a lot more technical answer to that as well about how various problems may be related to one another, but you need a PhD to start thinking about that.
Fantastic, thank you, Alex. Does anyone else have anything to add? Do you think dark matter is the first one that we're going to have more of an answer to?
I certainly hope so. I think there's an element as well of physicists having a slightly limited imagination. It's a thing that we don't fully understand, so let's call it dark.
Yeah.
Yeah.
Fab. Jarrett, Sally, would you like to add anything, or should we move on to the next question?
I think simply expanding the breadth of our knowledge will help inform answers to some questions and open up other questions. And so the more you know, the more you can know. So who knows if there's this connection to other mysteries, but probing some of these questions that are just tantalizingly out of our reach now, hopefully won't be out of our reach for much longer, will give us a new appreciation for the universe and allow us to then launch into tackling some of these other questions.
Yeah, I'd agree with everything everyone said, and I think it's also worth remembering that I think the time difference between when the Higgs boson was theorized and detected, I believe, is pretty similar to the dark matter story with WIMPs. So we're potentially getting to that sweet spot of a time difference there where we might actually finally see something, and we're all really hoping dark matter is the next big discovery.
Oh, absolutely, it's so exciting. Fantastic, thank you all for that. Next question, was it an accident when dark matter was first discovered? So I think that might mean first theorized or said, hey, there's a weird thing. Were we looking for something strange, or anyone want to answer that?
I can jump in. There were a few people who had sort of theorized dark matter earlier, but one of the big first names that you'll hear is a lady called Vera Rubin. And she was doing her PhD. She was looking at the orbits of various galaxies and stars within galaxies. And as we've said, we kind of understand how we think things should orbit. We understand how gravity affects the speed of a planet, particularly orbiting around a star. So she was thinking, well, we're just getting all this new data from these new fantastic telescopes that they were building in the 70s. I'm going to do the same thing, except I'm going to look on a bigger scale. I'm going to look at galaxies, and we're going to expect to see the nice exact same curve that we see for planets. The speed of planets, as you go further out, they get slower. And she started plotting it for a couple of, well, for one particular galaxy first. She plotted it and thought, oh no, this doesn't look the same. So, oh, maybe it's just one dodgy galaxy. Let's look at a few more. And she looked at a few more and found that all of them were not showing the same rotation curve. So it absolutely was a sort of accident breakthrough, as a lot of the fantastic breakthroughs in science are. You see some data that you can't explain with the things that you know, and then you have to come up with a new theory to explain that. And dark matter is the best explanation that we have for that phenomenon so far.
Fantastic, thank you, Ed. I can see Sally nodding along. Does anybody else have anything they'd like to add to that?
I'll just chime in and echo what Ed was saying, that it's so important to do good science. Some of these measurements are extremely difficult, and you can say, well, that's sort of close enough. But if you do the rigorous science and you chase the data to the logical conclusion, scientists are much more interested in finding a puzzle than they are, well, okay, it's close enough, let's go on and do something else. And so being able to do a careful measurement is extremely important to finding out possibly new science, right? It's motivating dark matter or motivating neutrinos, which are another type of really bizarre particle. isn't done by just sort of taking some casual measurements. It's a rigorous scientific process that really leads to, hey, this is different, this is strange, this is cool. Let's find out what it is.
Fantastic, thank you. All right, time is getting on. We've got so much more to talk about with dark matter. So I think we've probably got time for just two more questions. So the first one that I'll ask is, as with the LIGO gravitational wave detector, which gathers more information from having detectors at different locations around the Earth, the Boulby and Sanford underground research facilities in Italy and other places work together to do more than they can each do alone for some experiments. How does that collaboration work?
Sure, I can start off on that. It's really important to have multiple laboratories around the world. In terms of the science, there's a lot of benefit, and I know Alex was part of this as well with neutrinos, seeing signals of what you're looking for at different laboratories will make the discovery more robust. And so I mentioned neutrinos, but if someone sees dark matter at one laboratory, we'll want to be able to verify it with measurements at another laboratory. Getting back to the neutrinos for a second, if there's a burst, not likely to see a burst of dark matter particles necessarily in the near future, but if there was a burst, gravity is a burst, supernova neutrinos come in a burst, and so having that ability to look for a very rapid signal on a short period of time also really benefits from having a number of locations. I'll also finish up by just saying having contacts and discussions with facilities around the world allows you to pick out best practices. So you have this experiment that has these hazards, how do you manage those hazards? And being able to share, hey, this is what we did, or this is what we did, we ran into some issues here, and this is a better way. Being able to share lessons learned about how to support some of these really important experiments, including dark matter experiments, is really, it really requires lots of different people, lots of different facilities.
Thank you, Jarrett. Anything else to add in? Anybody else?
A couple of things, if I may. We haven't found dark matter yet, but if you look back historically, there's been many suggestions along the way where people see something funny and go, oh, could this be dark matter? Most recently, there's a hint of a particular sort of low energy excess in electron recoils, technical framing, but there's something which doesn't quite make sense in the most recent results from our xenon 1-ton experiment in Italy. And I don't think there's really a very strong suggestion. Well, there's lots of people who think this might be a hint for dark matter. To test if that's true, the critical thing will be to see whether or not a different experiment sees the same signal. And that's clearly going to be one of the first things that we're going after. The other side of the coin is, if you look at the latest instruments from Xenon and LZ, they're very similar. And that's not by accident. It's because even though we don't directly work together, we are jointly, collectively developing the technology, the best technology to take forwards. And it's the recent 10, 15 years or so, this general design of instrument has blazed the trail. It's orders of magnitude more sensitive than anything else.
Fab, thank you, Alex. Ed, did you have something to add?
Yeah, fantastic answer. I just wanted to really quickly add that even an individual detector is a massive international collaboration these days. Something might be designed in one country, might be built in one country. We had a part recently that was built in Europe. It was delivered to us in the UK. It went up to Scotland to be processed. It came back to us, and then it got shipped off to Canada. This is just a single part of a detector. It's all a massive international collaboration.
Yeah,
absolutely. Sally, did you want to add to that?
Yeah, so as well as, you know, confirming results by looking at between different labs, different experiments, hopefully seeing the same thing. There's also just the collaboration that we have, for example, between LZ, which lives at Sanford Lab, but a lot of the materials we used to build LZ were screened over at Boulby. So, you know, we had this process. I think Chris and Ed already touched on it, but we will find a material we want to use in LZ. We'll ship it over to the UK, and it'll go underground at Boulby. It'll get screened for radioactivity, and then we'll get a report from them and to telling us how much radioactivity is in it, so we can decide whether we use it or not. So like having collaborations like that, even just for one experiment, being able, you know, having the resources that Boulby has in that huge suite of these germanium detectors was really, really useful and productive. So.
Cool. All right. We haven't got very long, so I'll just ask one very last quick question. I'm so sorry that we haven't got to everybody's questions. There are some amazing ones here. So to what extent do you think that possible over and under densities in the dark matter distribution near Earth affects direct detection experiments? And what is the expected dark matter density around us? Who'd like to answer that one?
I can at least start with a very British description. I have heard it described as what we kind of expect the dark matter density to be around us, even though it actually depends on how heavy the particles are themselves. But a very generic guess is about 1 dark matter particle per pint glass. So if it is the evening in the UK, so if you're drinking a pint, you can assume there's about 1 dark matter particle in that.
That's a fantastic answer. Thank you, Sally. Anybody else?
It's worth mentioning as well that dark matter doesn't form the same shape as galaxies. So because of the way that we think that it interacts, dark matter is going to be more of a spherical sort of halo around an individual galaxy, whereas galaxies are often reasonably flat disks, that sort of shape. The dark matter isn't necessarily going to follow the same shape, so it won't vary as much in density as the normal matter does throughout a galaxy.
I think, may I also just add, there's a major satellite mission ongoing at the moment known as Gaia, which is measuring the speeds and locations of, I think it's 1 million stars in our galaxy. And it's doing so, you can imagine the dark matter moving around. If the dark matter's moving around within our galaxy, because there's so much more of it than the normal matter, you'd expect it to be influencing how the stars are moving around. So by measuring the positions and speeds of the individual stars, you can infer what the location and speed of the dark matter is. This is a project that's ongoing at the moment. It's delivering its first results now. And it seems to be suggesting that our general models for how the dark matter is distributed were basically correct. But as the next few years go by, that mission should hopefully tell us a lot more about exactly how the dark matter is distributed in our galaxy, which will help our measurements, because it'll tell us better what to be searching for.
Fab. Yep, Gaia is a fantastic mission. It's actually measuring 1 billion stars, not a mere million, 1 billion stars.
A cool 1,000 times more. Okay.
Yeah, absolutely. Jarrett, would you like to add anything to that final question?
No, that all sounds really exciting.
Brilliant. So thank you all so much to all of our speakers, to our panelists, and thank you especially to all of you who have joined us to talk about something that we clearly love so much, and we're so excited to share that with all of you. Just before I hand back over to Connie, we thought that we would ask you those questions that we asked at the beginning back at the end. So I'm going to launch polling. And then I think you should all be able to see those questions that I asked at the beginning. So do let us know what you think now. We're really interested to see if anything's changed. Do you think that dark matter research is too difficult for non-scientists to understand? Agree or disagree? Why do scientists go underground to study dark matter? Do they need to be in total darkness to shield their experiments, or because they believe there are more dark matter particles underground? And what % of mass and energy in the universe remains a mystery? All right. So just while you're answering that, I will say goodbye to the team down at Boulby, who are going to have to say goodbye and disappear now, because otherwise they'll get stuck underground for the rest of the night. They need to go and catch their cage back up. Bye-bye, Boulby. Thank you.
Thank you.
Okay. Oh, sorry, Ed.
Just saying thank you and goodbye.
Thank you very much. Good night. All right. Thank you so much for everybody that has voted in our polling. Panelists and other speakers, you'll be pleased to know that most people have been listening, and most people now do disagree that it's too difficult to understand. Thank you so much. That's all from me over in the UK and Oxfordshire. Good night to everyone on my side of the world, and I hope you have a lovely day, the rest of the world. Thank you for joining us, and thank you to all of our panelists. And I'll now hand over to Connie just to wrap us up. Thank you, Connie.
Are you ready for me, Matt? All right. Well, thank you all so much to our wonderful speakers, Ed and Jared and Sally and Alex, and to Sophie, who just did a fantastic job as our MC. This has been a great event. We're excited that you could all join us down here at the 4850 level and at the 3600 foot level in Boulby. I do want to remind some of our viewers of a couple of our next Deep Talk events going on. November 12th, we have 3 amazing neutrino scientists who are going to talk to us about the DUNE experiment, the Deep Underground Neutrino Experiment. And then on December 10th, we will be joined by Dr. Art McDonald, whose neutrino experiment at Snow Lab took a share of the Nobel Prize in Physics in 2015. So we hope you can join us all. And that invitation goes to everyone around the world. Thank you for being here with us, and I'll see you again soon.